Hello everyone, Statistical Thermodynamics we're going on, and in the last lecture we had mentioned the Boltzmann distribution law, which is applicable for the classical particles, and right now time for deriving this law. But before its derivation we have to learn about one mathematical trick which is known as the Stirling approximation, and this is the topic of today's lecture number 4. So what is the Stirling approximation? If some variable x which is very large, which has the very large value, in that case its factorial has larger value, and if you take the natural log of that factorial x, then its value, exact value, may be approximated to be equal to x ln x minus x. So this is the mathematical trick or the Stirling approximation. So this is some kind of approximation which would be applicable only when x is very large. So first of all we have to put some smaller values such as 6, 7, 8, 9, these values, and try to find out whether the left hand side is equal to the right hand side. So in this regard, this type of question you may have to face in your exam. Calculate the error percentage if the value of ln 6 factorial and ln 7 factorial are calculated by applying Stirling approximation. And the main thing is, what conclusion do you draw from the results? That means when the value of x increases, then the right hand side would be closer to the value of the left hand side. This result will be reflected whenever you will increase the value of x. So let's put the examples of 6, 7. For example, let us take x equals to 6. Okay, so what should be the value of left hand side, which is the exact value? This is the left hand side. Natural log of 6 into 5 into 4 into 3 into 2 into 1, that means natural log of 720, which is equal to 6.57925. Now what is the approximate value? If the Stirling approximation is applied to it, then what should be the value? It should be 6 ln 6 minus 6, and this value is equal to 4.75056. So it's much less than the original value. So what is the percentage of error? It is minus 27.8%. First of all, the difference between these two, then divided by the original value into 100. Okay, and since it is less, so the error is minus. Now if the value of x is increased by 1, instead of 6 if you take it to be 7, then by the similar process you will find that the left hand side is 8.5252, whereas the right hand side is 6.6214, and the error is found to be minus 22.64. That means around 5% of error has been eliminated. So you are approaching to the left hand side value when the value of x is increased. So instead of 7, if you take 8, it would be much more closer to the left hand side value. So from this you can draw a conclusion. What is the conclusion? That the percentage of error decreases with increasing value of x, and if x is very large, then the left hand side and right hand side becomes almost equal. So this approximation you have to use in the derivation of the Boltzmann distribution law. So in our next lecture, lecture number 5, we are going to derive the Boltzmann distribution law. But before that we have to make a typographic error of lecture number 3, where this slide was shown, remember, and this value was shown to be n epsilon, isn't it? But just make this make the correction of this typographic error. This is not n epsilon, this is not the nth excited state, this is the ith excited state. So the value should be actually I epsilon. Here I epsilon, here also I epsilon. So the corrected value should be like this. Okay, so it is I epsilon. So make this little correction. Okay, this is typographic error. So that's all for this lecture number 4. Thank you and have a nice day.